for our second semester syllabus. Now, in the last classes, we have discussed types of waves. So now we will discuss type of wave motion. That is, basically there are two types of wave motion: transverse, where particles of the medium vibrate at right angles to the direction of propagation of the wave; longitudinal, where particles of the medium vibrate parallel to the direction of propagation. Now, here there are two things. One is when the particles are moving perpendicular to the vibration propagation. If the wave is moving like this, the particles will have this type of, that is perpendicular to the direction of propagation. And secondly, longitudinal waves, where they are parallel to the direction of wave propagation. Now, sound waves, waves along a string, or those type of waves are basically longitudinal waves in nature. So now when you discuss a wave, it could be a time displacement curve or a space displacement curve. Here, when you say displacement, see, the wave is traveling through a medium. We know wave is nothing but a disturbance. So what happens? The particles in the medium move to and fro about their mean position, and that is known as the displacement. So here, generally we will draw a space displacement curve as wave travels a distance. Now here, what is a space displacement curve? Gives the shape or form of the wave, and this is known as waveform. Suppose a wave is constant throughout, like constant, the same shape, then you will call a constant waveform shape. It's a constant wave, and because it is repeating itself, it can be called as a periodic wave also. Now let us talk about some basic definitions in waves. What are the basic parameters? See, we are having a wave like this. The point of maximum here, that is known as the amplitude of the wave, that is represented by A. Now look at point C, D or A, B. So these points are actually corresponding to the same points here, and they are said to be in same phase. So these same phase points, when the distance between these two same points is known as lambda, and time taken to cover one complete cycle, that is a wave is going here, coming here, and again repeating itself, and this part is known as the time period. So here we have discussed, that is time needed to for the generation of a one complete wave is known as time period, and these are the same phase points. We can take one point here also, when one point corresponding point here, it is also a same phase point. Now moving forward, now we will define what is a frequency. Frequency is n or nu in some textbooks. It is number of complete waves produced in a medium per second. So frequency is given by 1 by time period. Amplitude is the maximum displacement of a particle on the path of the wave. So a particle, you know, a particle, when a wave is moving through a medium, wave is a disturbance through a medium. The particles don't sit in their same position, they move back and forth, and that maximum displacement is known as the amplitude of the wave. Again, one thing which we have left is, what will be velocity? Velocity in the of the wave in that medium. So is that, we know velocity is distance by time. In this case, we are taking lambda as distance by the frequency, by the time period. It is lambda by t. So we can also be written as lambda, and we know 1 by t is nu. So this is again a very basic definition which you know already. So here we, for convenience, if you are confusing between v and nu, you can write down this as c also. But again, since we are using c for a speed of light, we will use v for users. Now here we have again discussed lambda is the shortest distance between any 2 points on the path of the wave having same phase of vibration. Now the phase difference between two oscillating particles on the line of propagation separated by lambda is 2 pi radian or 360 degrees. See, suppose this has the same phase, this has the same phase, this has the same phase, and this is known as lambda, and the phase is that 360 degree. For a sinusoidal wave, means it is repeating itself. That is this and this, when they are separated by a distance of lambda, that is the phase difference is known as 360 degrees. Now here, moving further, So the phase difference per unit distance will be 2 pi by lambda. We know total phase distance for a distance of lambda is 2 pi. Then for unit distance it will be 2 pi by lambda. For a distance x it will be 2 pi by lambda x. For a distance x. For a distance x it will be what? 2 pi by lambda x. This is pure mathematics, nothing else. Now here we were discussing about progressive waves. So we will discuss about the characteristics of progressive waves. Is that waves are produced by the periodic vibrations of particles in the medium. Each particle oscillates about its mean position with same A and T, same amplitude and time period, like in a simple harmonic motion, that is to and fro motion. The wave is a disturbance the particles move to and fro, that is the simple harmonic motion. Now moving further, what we realize is that the medium as a whole does not move. Wave is a disturbance. So wave is the one which moves and the wave is the one which carries the energy. That we also know because that is the property of these waves. That is they travel energy in the direction of propagation. So you are having a medium with lot of particles. You are creating a disturbance. There is a to and fro motion. And the medium is not getting traveled. The energy is traveled across the medium. Now we will go with the mathematical expression of a plane progressive wave. Now what will be the mathematical expression? That let us consider psi as the disturbance associated with the wave whose value changes with time t. That is with time. When the wave is traveling, it will not be, so there will be a passage of time. So what happens? Let us see. So consider the wave to be at point here. What you do? Let us name this point as x. And at time t is equal to 0. See, at time t is equal to 0, the value of psi is psi x is 0 because t is 0, which can be written as a function of x, capital X. This is capital X, where x is the position coordinate measured from arbitrary origin. Let us take this from the arbitrary origin x at time t is equal to 0. Now this is fx. Now what happens? It is after some time it will travel a distance vt, where v is the velocity and t is the time. So t will not be 0 always. No, after some time the wave has traveled a distance. So what is the distance it has traveled? So this was x plus vt. So it can be written as small x. So what happens? This is capital X. This is capital X. Now what happens to this point? This point is what? Small x, which is capital X plus vt. Or we can write down in another way. Write down. So what will happen? This can be written as, since the wave function is constant and the same function psi after time travels a distance vt, let us say, is given by psi x0 is equal to f of x is equal to f x minus vt. Now what is this x? X is this is small x minus vt, such that psi can be represented at small xt. This is nothing wrong. See, the wave is remaining like that. Look at this point here. The wave is moving in this direction. Initially at time t it was at a position x. It has traveled a distance vt. So the new position is x plus vt, capital X plus vt. And that is known as small x position. Now when we want to write it in that position, we want to express in terms of x only, because earlier it was f of x. Now what is this x? X has become x minus vt when it is traveling towards right. That is the positive direction. Now what happens? So therefore x of 0 is f of capital X, which is after some time it will become, this x becomes what? X minus vt, small x minus vt, and psi is a function of x and t. The same wave function is constant, the wave is same, but after some time it becomes xt, where v is the velocity. Now the function fx minus t represents a progressive wave moving in the positive x direction. Same is the case with the negative. See, the wave is moving towards left. So if this was the position and this was the origin, then this position will be minus vt. So the new position will be small x is equal to capital X minus vt, such that the new fx comes out to be what? fx plus vt, that is wave traveling in the negative direction. Now I hope this is very clear. When a wave is traveling in the positive direction, it is given by x minus vt, and the wave is traveling in this direction. This is the positive direction. And the disturbance, let us say, traveling in this direction, it is given by x plus vt. When it is traveling towards left, it is towards the negative of the axis. So actually this x become x minus vt, hence the small x plus vt. I hope this part is very clear. This is something you must be wondering when we write the wave equation, why we write this x minus vt and x plus vt. This is the basic reason for that. Now here, what we realize that you can exchange x and ct such that ct minus x and x minus ct can be written represents the same plane progressive. So here this is this function, since it is a function, we are writing expressed in terms of function. So x minus ct and ct minus s can be written. Some textbooks write it that way also. So there is nothing new, because since it represents a wave and it is okay to write it. Now here there will be fx minus vt has some following characteristics. Is that at particular instant of time x minus vt, and hence fx minus vt remains the same. This quantity is called the phase. Now here see, when the wave is traveling, look here, t changes. What happens? X is also changing. So what does that mean? That means this fx minus x minus vt and fx minus vt remains the same. See, the wave is moving in the right direction. Wave is not decaying, wave is moving. So what is happening? The distance is changing, time is changing. So what will happen? The time is increasing, this is increasing. So this difference x minus vt will remain the same. Hence this quantity x minus vt is called the phase. Same is the case when it is in the opposite direction. What will happen? That is x plus vt. Then what will happen? It will represent the plane wave propagating in negative direction. Here what happens is that when t increases, second case x plus vt, is that when t increases, x should decrease. Then only x plus vt will remain constant when it is traveling in these directions. For the time being, let us only consider this. So with increasing time, phase remains constant. So with the same waveform, if the waveform is same, then the phase is constant. So that's it. That is the thing which I wanted to discuss today. So thank you.